Mars is dead, but once, oceans rippled across its surface. Once, rivers carved through ancient stone. Once, this world could have been home, and we know exactly who killed it. Look at Mars today and you see rust, dust, a frozen wasteland where temperatures plunge to minus 120 degrees Celsius on a calm night. The air is so thin you could stand on the surface and your blood would boil. Not from heat, from pressure, or rather, the complete lack of it. Earth's atmosphere pushes down on you with the weight of an invisible ocean. Mars? It has almost nothing, less than 1% of what we breathe. You'd suffocate in seconds, even if you held your breath. But here's the thing, this dead world wasn't always dead, and the evidence is everywhere. Before we dive deeper into this story, make sure you hit that subscribe button and smash that like. We're about to uncover one of the greatest mysteries in our solar system, and trust me, you won't want to miss what comes next. The red planet earned its name honestly. When you look at Mars through a telescope, you see a world painted in shades of ochre and rust. Iron oxide. The same stuff that turns old nails orange when they sit in the rain. Except on Mars, the entire planet is one giant junkyard of oxidized metal. The dust gets everywhere. The storm feeds on itself, growing larger, spinning faster. Within days, a regional dust storm can engulf an area the size of North America. And sometimes, maybe once every few years, the storm goes global. The entire planet disappears under a veil of airborne rust. During the Great Dust Storm of 2018, NASA's Opportunity rover sent its light. It never woke up. That storm lasted for months. By the time the dust settled, Opportunity was gone, buried under Martian soil after exploring the planet for nearly 15 years. But here's what makes Martian dust storms truly alien. On Earth, a storm that size would sound like the end of the world. Thunder, howling wind strong enough to strip bark from trees. On Mars, the wind screams at hundreds of kilometers per hour, but you'd barely feel it. The atmosphere is so thin that even hurricane-force winds can't knock you over. They'd feel like a gentle breeze. The dust would kill you, sure, blocking out the sun, clogging equipment, getting into every seal and joint. But the wind itself? Harmless. It's like being punched by a ghost. The temperature swings are just as brutal. Stand on the Martian equator at noon, and the ground beneath your feet might reach a pleasant 20 degrees Celsius. Spring weather. But your head? Just 2 meters up? Freezing. The thin atmosphere can't hold heat. It can't distribute warmth. So temperature drops with altitude faster than you can imagine. And when night falls, everything plummets. That same spot that felt almost comfortable at noon? Minus 70 by midnight. Minus 100 in the polar regions. Cold enough to freeze carbon dioxide out of the air. Cold enough to turn the atmosphere itself into snow. And the radiation. Oh, the radiation. Earth has a shield. A magnetic field generated by molten iron churning in our planet's core. That field deflects most of the solar wind, those charged particles constantly streaming from the sun. Mars had that shield once. We know because the rocks remember. But about 4 billion years ago, something happened. The dynamo in Mars's core shut down, the magnetic field collapsed, and suddenly, the Martian atmosphere stood naked against the sun's fury. Without that shield, cosmic rays slam into the surface unimpeded. A human standing on Mars would absorb radiation equivalent to getting a full-body CT scan every few days. It would damage DNA, increase cancer risk, break down complex organic molecules. If you tried to live there unprotected, the radiation alone would probably kill you before the cold or the lack of oxygen got their chance. This is Mars today, a world that seems designed to destroy anything foolish enough to land on its surface. But it wasn't always this way, and that's where the story gets interesting. The Chinese Zhurong rover touched down on Mars in May of 2021. It landed in Utopia Planitia, a vast plain in the northern hemisphere. Just another flat, dusty expanse, or so it seemed. The rover carried ground-penetrating radar. Think of it as an ultrasound for planets. It sends radio waves into the ground and listens for echoes. Different materials reflect those waves differently. Ice looks different from rock. Loose sediment looks different from solid bedrock. And what Zhurong found beneath the Martian surface changed everything. The radar revealed layers, not random layers, organized strata tilted at a gentle angle, sloping down toward the north. The pattern was unmistakable. These were coastal deposits, the kind you'd find on Earth, where rivers meet the ocean, where waves lap against an ancient shore. The radar traced these deposits for over a kilometer as the rover drove north, continuous, uninterrupted, exactly what you'd expect from a coastline. Scientists estimate these deposits are about 3.5 billion years old. Back when Earth was still figuring out how to build complex life. Back when our planet's oceans teemed with nothing more sophisticated than bacteria, Mars had an ocean of its own. Oceanus Borealis, they call it now. The Northern Ocean. It would have filled the entire northern lowlands of Mars, covering nearly a third of the planet's surface. Imagine an ocean the size of Earth's Atlantic and Pacific combined. Water stretching from horizon to horizon, waves rolling across a Martian sea.
The evidence doesn't stop with Zhurong's radar. Orbital observations have spotted what look like ancient shorelines. These aren't simple straight lines. They're complex, showing signs of multiple water levels over time. The ocean must have fluctuated, rising and falling with Mars's climate. And scattered across the old seabed, we find minerals that only form in the presence of water. Clays, sulfates, carbonates, the chemical fingerprints of a wet world. But here's the part that sends chills down my spine. The delta deposits. Scientists found massive delta formations where ancient rivers once emptied into that primordial ocean. A river delta works like this. Water flows downhill, carrying sediment, rocks, dirt, everything it can move. When that river reaches still water, a lake or ocean, it slows down. The sediment drops out. Over thousands of years, layer after layer builds up. The pattern is distinctive, fan-shaped, stratified. And we've found dozens of these deltas around what would have been the northern ocean's edge. The Perseverance rover landed in Jezero crater specifically because orbital images showed a delta there. A massive fan of ancient sediments that could only have formed if Jezero was once filled with water. A lake fed by rivers that flowed from the southern highlands. When Perseverance drilled into rocks from that delta, it found exactly what geologists predicted: layered sedimentary rocks. The kind that form when silt settles out of calm water. The kind that could preserve signs of ancient life. Think about what this means.
3.5 billion years ago, Mars had liquid water on its surface. Lots of it. An entire ocean, rivers, lakes, maybe rain. The planet must have been completely different. To keep water liquid, you need two things. Temperature above freezing, obviously, and enough atmospheric pressure to stop that water from immediately boiling away into space. Which means ancient Mars must have had a thick atmosphere, thick enough to trap heat, thick enough to create a greenhouse effect that kept the surface warm. How thick? Scientists estimate the ancient Martian atmosphere could have been 10 times denser than today, maybe more. Dense enough to support weather systems, clouds, perhaps even a water cycle, where ocean water evaporated, formed clouds, fell as rain in the highlands, and flowed back to the sea through river systems. A living, breathing hydrological cycle, just like Earth. The water wasn't just sitting there either. We have evidence of massive floods, outflow channels carved into the Martian surface that could only have been created by catastrophic releases of water. Picture this: underground ice, kept solid by the cold. Volcanic activity heats the region. The ice melts suddenly, all at once. Billions of tons of water burst from the ground, carving valleys hundreds of kilometers long in a matter of days. The flood channels on Mars dwarf anything on Earth. They're so large that early astronomers thought they were seeing evidence of Martian canals. They were right about the water, just wrong about who built them. Some of these floods may have triggered tsunamis in the Northern Ocean. In 2016, scientists reported finding deposits consistent with megatsunamis. Waves potentially hundreds of meters high, triggered by asteroid impacts into the ocean. The waves crashed onto shore, dragged boulders inland, and left behind debris fields that we can still detect from orbit billions of years later. Try to picture it.
a massive asteroid slamming into the Martian Ocean. The impact vaporizes millions of tons of water instantly. A wall of water radiates outward at hundreds of kilometers per hour. It crashes onto the shore, sweeping everything before it, carrying rocks the size of houses kilometers inland. And when the water finally recedes, it leaves behind a chaotic mess of boulders and sediment that forms a layer we can identify today. But perhaps the most compelling evidence comes from the isotopes. Isotopes are variants of the same element with different atomic weights. Water, for example. Most water molecules contain regular hydrogen, but some contain deuterium, a heavier version of hydrogen. Deuterium is harder to strip away from a planet because it's heavier. So if you lose a lot of water to space over billions of years, the remaining water gets enriched in deuterium. It's like if you had a jar of marbles, some light and some heavy, and you started shaking them out. The light ones would leave first. Eventually, you'd have more heavy marbles left than you started with. Scientists measured the deuterium to hydrogen ratio in Mars's atmosphere. They found it's enriched by a factor of about 7 compared to Earth. This tells us Mars has lost enormous amounts of water. Based on the enrichment factor, scientists estimate ancient Mars had enough water to cover the entire planet to a depth of over 100 meters. If you concentrated all that water in the northern lowlands, you get an ocean up to a mile deep in places. An ocean that could have persisted for hundreds of millions of years, maybe longer. And during that time, Mars might have been habitable. The temperatures would have been right. The water was there. The chemistry was there. We found the essential elements for life embedded in Martian rocks. Carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur, everything you need. On Earth, life appeared almost as soon as conditions allowed. The oldest fossils we've found are 3.5 billion years old, the same age as Mars's ocean. If life is as inevitable as it seems, then Mars should have developed life too. Simple microbial life, bacteria, maybe something more complex. We don't know yet, but the possibility haunts every mission we send there. So what happened? How did this wet, potentially habitable world turn into the frozen desert we see today? The answer lies in what Mars lost, and it starts with the core. Deep beneath your feet, Earth's core churns with molten iron. The planet's rotation and the convection of that liquid metal create electric currents. Those currents generate Earth's magnetic field. It's a dynamo powered by the heat left over from our planet's formation. The field extends far into space, creating a protective bubble called the magnetosphere. When the solar wind hits this bubble, it deflects around us. Most of it never touches our atmosphere. Mars had this too. We know because scattered across the Martian surface, particularly in the southern highlands, we find rocks that are magnetized, frozen magnetic fields locked into stone billions of years ago. These rocks point in different directions, creating a patchwork of local magnetic fields. It's like the planet tried to create a magnetic field, but only managed it in pieces, a broken shield that couldn't protect the whole world. Scientists think Mars's magnetic field collapsed around 4 billion years ago. Something went wrong in the core. Maybe it cooled too quickly. Mars is smaller than Earth, only about half our diameter. Smaller planets lose heat faster, like how a cup of coffee cools quicker than a whole pot. When the core cooled enough, the convection stopped. The dynamo shut down. The global magnetic field died. Recent research suggests the collapse might have been even more complex. Studies of Martian meteorites and data from the InSight lander indicate the core might have separated into layers of immiscible liquids. Like oil and water, they don't mix. One layer, rich in sulfur, another, rich in hydrogen. When these layers settled out, the convection that powered the magnetic field weakened and eventually stopped. The core essentially died, and with it, Mars's primary defense against the sun. Without a global magnetic field, the solar wind began stripping away the atmosphere. Here's how it works. The solar wind isn't just particles. It's magnetized plasma, carrying magnetic fields from the sun. When this magnetized plasma hits an unprotected atmosphere, it can create electric fields. These fields accelerate ions, charged particles in the upper atmosphere, giving them enough energy to escape into space. It's called atmospheric sputtering, and it's devastatingly efficient over geological timescales. The MAVEN spacecraft, which has been orbiting Mars since 2014, measured this process in action. It watched as the solar wind stripped away about 100 grams of atmosphere every second. That doesn't sound like much, but multiply it by billions of years. The math is brutal. Mars has lost roughly 66% of its original atmosphere to space. 2/3 of the air that once wrapped around this planet is now drifting somewhere in the solar system, never to return. And it gets worse during solar storms. When the sun belches out a particularly strong burst of radiation and particles, the rate of atmospheric loss increases dramatically. MAVEN observed this during a solar storm in March 2015. The escape rate jumped by a factor of 10 or more. Imagine if ancient Mars, with its young and violent sun, experienced solar storms far more frequently than today. The atmospheric erosion would have been relentless. As the atmosphere thinned, the greenhouse effect weakened. Less carbon dioxide in the air meant less heat trapped at the surface. Temperatures dropped. The water cycle began to fail. Lakes froze. Rivers stopped flowing. And here's the cruel feedback loop. As surface water froze and got buried under dust, it removed even more gas from the atmosphere. Water vapor is a greenhouse gas. Less water vapor means less warming, means more freezing, means less water vapor. The planet spiraled into a death cycle it couldn't escape. Some of the atmospheric carbon dioxide froze out at the pole. Even today, Mars's polar ice caps aren't just water ice. They're layered with frozen carbon dioxide, dry ice that sublimates and refreezes with the seasons. During Martian winter, up to a quarter of the atmosphere freezes onto the poles. In summer, it sublimates back into gas. The entire atmosphere breathes with the seasons. But it never comes back to what it was. The bulk of it is gone, lost to space forever. The nitrogen tells a similar story. Earth's atmosphere is mostly nitrogen. Mars's ancient atmosphere probably had a lot of nitrogen too. But nitrogen is lighter than carbon dioxide, easier to strip away. Scientists measured nitrogen isotopes in the Martian atmosphere and found massive enrichment in the heavier isotope, nitrogen-15. The math suggests Mars has lost about 75% of its nitrogen, even more than the carbon dioxide. The planet's original atmosphere would have been substantially thicker and richer than anything we see today. And now, it's just gone. But it's not like Mars gave up without a fight. Even without a global magnetic field, the planet has an induced magnetosphere. The solar wind, carrying its own magnetic field, piles up against the upper Martian atmosphere. This creates currents in the ionosphere, and those currents create their own magnetic field. It's not as strong as Earth's, not nearly as effective, but it provides some protection. Recent studies show this induced field actually shields the lower atmosphere better than scientists expected. It's not enough to stop the long-term loss, but it slows it down. The crustal magnetic fields, those remnants of the ancient global field, also help in small ways. In regions where the crustal field is strong, it can deflect some solar wind particles, creating miniature magnetospheres. These tiny protective bubbles don't cover much of the planet, but in the areas they do protect, atmospheric loss is reduced. It's like having a handful of umbrellas during a torrential rainstorm. Better than nothing, but nowhere near adequate. The transformation must have taken hundreds of millions of years. Mars didn't die overnight. There would have been periods of stability, maybe even brief rebounds, when volcanic activity pumped fresh gas into the atmosphere. But the trend was inexorable. Down. Always down. The ocean evaporated or froze. The rivers dried up. The rain stopped. And eventually, Mars became the sterile, frozen world we see today. A cautionary tale written in rust and ice. But the dead don't always stay quiet. And Mars has one more surprise to share. Because even in death, this world refuses to be ordinary. If you thought Earth had impressive mountains, wait until you hear about Olympus Mons. This isn't just the tallest volcano on Mars, it's the tallest volcano in the entire solar system. The peak rises almost 22 kilometers above the surrounding plains. That's nearly 2.5 times the height of Mount Everest. But here's what makes it truly alien. You couldn't see it from the base. Not really. Olympus Mons is a shield volcano. which means it's not a steep cone like Mount Fuji or Mount St. Helens. Instead, imagine a mountain the size of France, 600 kilometers across. So wide that if you stood at the base and looked toward the summit, the peak would be beyond the horizon. The slope is so gentle, averaging only about 5 degrees, that you could probably walk up most of it without realizing you were climbing a mountain at all. The Martian horizon curves away before the summit comes into view. You'd be standing on the largest mountain in the solar system and wouldn't even know it. The caldera at the summit tells the story of this giant's formation. 6 nested craters collapsed into one another over millions of years of eruptions. Each crater formed when magma drained from chambers beneath the summit, leaving a void that the surface then collapsed into. The complex of calderas spans 80 kilometers by 60 kilometers and reaches depths of over 3 kilometers. Standing on the rim of one of these calderas would be like standing at the edge of a cliff that drops down into darkness for twice the depth of the Grand Canyon. What makes Olympus Mons and the other Martian volcanoes grow so massive? The answer is simple and profound. Mars doesn't have plate tectonics. On Earth, volcanic hotspots stay fixed in the mantle, while tectonic plates slide over them. This creates island chains like Hawaii. Each island forms over the hotspot, then the plate carries it away, and a new island begins forming. On Mars, the crust doesn't move. A volcano sits over its hotspot for billions of years, building layer upon layer upon layer. The mountain just keeps growing until the volcano finally goes dormant. And Olympus Mons might not be completely dead. Crater counting on the northwestern flank suggests some lava flows could be as young as 2 million years old. That's recent in geological terms. A blink. It's possible this giant could erupt again, though probably not for millions of years. But the fact that it could erupt at all means Mars isn't completely geologically dead. There's still heat in that core, still magma moving beneath the crust. The planet breathes, just very, very slowly. The cliffs surrounding Olympus Mons are another mystery. A scarp up to 8 kilometers high rings parts of the volcano's base. These cliffs are so tall that they make the cliffs of Dover look like speed bumps. Scientists think they might have formed from massive landslides. Imagine the flank of the volcano becoming unstable under its own weight. Billions of tons of rock suddenly let go, sliding outward in a catastrophic avalanche. The debris would have spread for hundreds of kilometers across the surrounding plains. Some of the largest landslides in the solar system probably happened right here, carving these spectacular cliffs from the base of the mountain. But Olympus Mons isn't alone. Just to the southeast, you'll find the Tharsis Montes, 3 more massive shield volcanoes arranged in a nearly straight line. Arsia Mons, Pavonis Mons, Ascraeus Mons. Each one is taller than any mountain on Earth. Together with Olympus Mons, they sit atop the Tharsis Bulge, a massive dome of crust pushed up by volcanism from below. The bulge itself is staggering, 8,000 kilometers across, 8 kilometers high at the center. It's like someone inflated a bubble beneath the Martian crust, and these volcanoes are the pimples that formed on top. The Tharsis Bulge formed over billions of years as magma pushed up from deep within Mars. The weight of all that volcanic rock, all those massive mountains, stressed the crust. And eventually, the crust cracked. Those cracks radiate outward from Tharsis, like fractures in a windshield. But one of those cracks grew into something spectacular. Something that makes the Grand Canyon look like a scratch. Valles Marineris. The name means Mariner Valleys, named after the Mariner 9 spacecraft that first photographed it in 1971. But calling it a valley feels inadequate. This is a system of canyons that stretches 4,000 kilometers along the Martian equator. That's roughly the width of the United States from Los Angeles to New York. In places, it's 200 kilometers wide, deep enough that if you stood on one rim, the opposite rim would be beyond the horizon. And the depth reaches up to 7 kilometers. That's 4 times deeper than the Grand Canyon. Scientists think Valles Marineris started as a rift. As the Tharsis Bulge swelled, it stretched the crust to the east. The rock couldn't handle the stress. It cracked. That initial crack became a weak point, and water, wind, and landslides widened it over billions of years. The canyon system shows clear evidence of erosion by flowing water, channels that could only have been carved by ancient rivers, layered sediments that settled out of standing water, minerals that form in wet environments. Some parts of Valles Marineris may have been isolated lakes at various points in Martian history. As the canyons filled with water, they would have created long, deep lakes nestled between towering cliffs. The water would have been calm, protected from the wind by the canyon walls, perfect conditions for sediments to settle in neat layers. Perseverance and other rovers have found these layers elsewhere on Mars, and orbital imaging suggests similar layering exists in Valles Marineris. If we could drill into those layers, we might find a record of Martian climate preserved like pages in a book, each layer representing a different era: wet periods and dry periods, times of hope and times of death. The western end of the canyon system opens into chaos terrain, Noctis Labyrinthus, a maze of intersecting canyons, pits, and fractured ground. It looks like someone took a sledgehammer to the crust. Scientists think this region formed from a combination of tectonic stress and catastrophic groundwater release. Imagine vast reservoirs of ice and liquid water trapped beneath the surface. Volcanic heat melts the ice suddenly. The ground collapses as the water rushes out. What's left is a chaotic mess of broken crust, a geological nightmare that stretches for hundreds of kilometers. And recently, scientists discovered something unexpected in Valles Marineris: volcanoes. More than 100 small volcanic cones on the eastern floor of the canyon system, in an area called Copertes Chasma. They're tiny compared to Olympus Mons, only about 400 meters high, but they're young. Crater counting suggests they're between 200 and 400 million years old. That's incredibly recent for Mars. Most volcanic activity on the planet shut down over 3 billion years ago. These little volcanoes prove that Mars's geological engine was still running, still producing magma, long after the planet was supposed to have gone cold. The discovery also raises intriguing possibilities about habitability. Where there are volcanoes, there's heat. Heat means energy. Energy means the potential for liquid water, even in a frozen world. The rocks around these Copertes volcanoes show signs of alteration by hot water. Minerals like opal that form when heated water percolates through rock. If there was volcanic heat and water together, even recently by geological standards, then there could have been habitable environments. Warm, wet pockets beneath the surface where microbial life might have survived, even as the surface froze. Valles Marineris and the Tarsis volcanoes are connected in ways we're still trying to understand. The canyon system lies directly east of the Tharsis Bulge. The stresses that created the bulge also created the canyon. The volcanic activity that built the mountains may have provided the heat that released groundwater, carving the canyons deeper. It's all part of one massive geological system that shaped half a planet. And it's still shaping Mars today, just much more slowly. Landslides still occur in Valles Marineris. We've detected recent slides from orbit, fresh scars on the canyon walls where millions of tons of rock slumped downward. The canyon is still evolving, still changing, even now. In a billion years, it might be unrecognizable, wider, deeper, more complex. A scar that keeps growing on a world that refuses to heal. Walking through Valles Marineris would be like walking through a cathedral built by geological time. The walls tower kilometers above you, layered in different colors based on composition and age. Red iron-rich layers, dark volcanic basalts, pale sedimentary rocks that formed in ancient water. The scale would be overwhelming, incomprehensible to human perception. You'd need hours just to walk from one wall to the other, assuming the terrain was even passable. And looking up at those walls, you'd be staring at billions of years of Martian history laid bare, a vertical slice through time itself. But as spectacular as these geological wonders are, they're not what drives our current obsession with Mars. Because scattered across this dead world, we're finding clues that it might not have always been dead. And some of those clues suggest it might not be completely dead, even now. In November of 2024, NASA's Curiosity rover was driving across a patch of Martian ground in Gale Crater. Just another day after more than 12 years on the surface. The rover's wheels rolled over a rock. The rock split open, and inside,
scientists saw something they'd never seen before on Mars. Bright yellow crystals, pure sulfur, elemental sulfur in crystalline form. Sulfur is common on Mars. We find sulfur compounds everywhere. Sulfates, sulfides, but pure sulfur? That's rare. On Earth, you find it around volcanic vents and hot springs,
places where geological activity brings sulfur up from the depths. The discovery raises an obvious question. If there's pure sulfur on the surface of Gale Crater, what geological processes put it there? And more importantly, what else might be hidden beneath the Martian dust? Curiosity has been exploring Gale Crater since 2012. The crater is 150 kilometers wide, formed by an ancient asteroid impact. But what makes it special is Mount Sharp, a 5-kilometer-tall mountain of layered sediments rising from the crater's center. Those layers represent billions of years of Martian history. The rover has been slowly climbing that mountain, drilling into different layers, analyzing their chemistry, reading the story written in stone. And the story keeps getting more interesting. Curiosity found organic molecules, carbon-based compounds that, on Earth, are often associated with life. Things like benzene and propane locked in rocks 3 billion years old. Now, organic molecules don't necessarily mean life. They can form through non-biological processes, but they're the building blocks life uses. Finding them in abundance is encouraging. More recently, Curiosity detected methane in the Martian atmosphere. Not a lot, just a few parts per billion, but it varies seasonally, rising and falling in a pattern that suggests an active source. On Earth, most atmospheric methane comes from biological sources. Bacteria produce it as waste, but it can also come from geological processes, like reactions between water and certain minerals. Scientists don't know which explanation is correct for Mars. Maybe both, maybe neither. The mystery remains unsolved. Then there's Perseverance, the newer rover that landed in Jezero Crater in February 2021. Its mission is explicitly focused on looking for signs of ancient life. Jezero was chosen because orbital imaging revealed that massive delta formation, evidence of an ancient river emptying into what was likely a lake. If life existed in that lake, the sediments in the delta might preserve fossils or chemical signatures. In July of 2024, Perseverance drilled into a rock the team nicknamed Chayava Falls. The sample came from ancient mudstone in an area called Neretva Vallis, an old river channel. When the rover's instruments analyzed the sample, they found something extraordinary. Organic carbon arranged with phosphate, iron, and sulfur in distinct, repeating patterns. And embedded in the rock, leopard spots, circular features that, on Earth, form when microorganisms alter their environment as they grow. Two specific minerals caught scientists' attention: vivianite, in iron phosphate, and greigite, in iron sulfide. Both minerals are associated with biological activity on Earth. Bacteria use iron and sulfur for metabolism, and when they do, they create these kinds of minerals as byproducts. The patterns in the Chayava Falls sample match what we'd expect from microbial activity, but they could also form through unknown geological chemistry. We simply don't know Mars well enough yet to say for certain. The sample is now sealed in a tube, one of 24 samples Perseverance is collecting. The plan is to leave these samples in a cache on the Martian surface for a future mission to retrieve. A sample return mission that would bring Martian rocks back to Earth for analysis in laboratories with instruments far more sophisticated than anything we can send to Mars. The Chayava Falls sample is potentially the most important rock humanity has ever studied. If it contains evidence of life, even ancient, extinct life, it would answer one of the most profound questions we've ever asked. Are we alone? But here's the frustrating part. We can't know for sure without getting those samples back to Earth. And the Mars sample return mission has been plagued with delays and budget overruns. NASA's latest plans suggest the samples won't return until the 2030s at the earliest, maybe later. So the potential evidence of life on Mars sits in a tube on the surface of Jezero Crater, waiting, tantalizingly close and impossibly far at the same time. Even if the Chayava Falls sample turns out to be geological rather than biological, the search continues. Mars has proven over and over that it was habitable once. Liquid water, essential elements, energy sources, everything life needs. The question isn't whether Mars could have supported life. The question is whether it did. And if it did, whether any of it survived the planet's transformation into the frozen desert we see today. Because there's another possibility that keeps astrobiologists awake at night. What if life still exists on Mars? Not on the surface, obviously. The surface is sterilized by radiation and desiccated by the thin atmosphere. But below the surface? That's a different story. We know there's ice beneath the Martian surface, lots of it. If there's ice, there could be liquid water too, in places where geothermal heat keeps the temperature just right. And where there's liquid water and energy, there might be life. Hardy, tenacious, clinging to existence in underground pockets far from the deadly surface. We wouldn't be the first life in the solar system, just the first to build rockets. The Viking landers tried to answer this question back in 1976. They carried experiments specifically designed to detect Martian microbes. One experiment added nutrients to Martian soil and watched for signs of metabolism. Another looked for organic molecules. The results were confusing. Some tests came back positive, others negative. Scientists argued about the data for decades. Most now think the Viking experiments detected unusual chemistry rather than biology, but we're not entirely certain. The question remains open. What we need is to drill deep. The surface of Mars is hostile, but 10 meters down? 100 meters down? The environment could be completely different, protected from radiation, stable temperature, possibly even liquid water and aquifers. This is where future missions are headed. Drilling rigs capable of penetrating deep into the Martian subsurface. Looking for water, looking for organic chemistry, looking for life. And the technology is finally catching up to the ambition. But water isn't just important for life, it's essential for human survival. And if we're going to send people to Mars, we need to know where the water is and how to get it. The Mars Reconnaissance Orbiter has been circling the planet since 2006, taking high-resolution images of the surface. In 2015, scientists noticed something strange in photos of certain steep slopes. Dark streaks that appeared during warm seasons and faded during cold periods. These features, called recurring slope lineae, seem to flow downhill like water. But water can't exist as a liquid on the Martian surface for more than a few seconds before it either freezes or evaporates. So what were they? Spectroscopic analysis detected hydrated salts in these streaks, perchlorates mixed with water molecules. On Earth, perchlorates can lower the freezing point of water dramatically. Salty brine can stay liquid at temperatures well below 0 Celsius. The hypothesis was tantalizing. Maybe these dark streaks were seasonal flows of extremely salty water, seeping from underground sources, flowing briefly down slopes during the warmest parts of the Martian year. But the story got complicated. More recent studies suggest the streaks might be granular flows, dry avalanches of dust and sand triggered by frost sublimation rather than liquid water. The debate continues. Some scientists still think there's briny water involved. Others are convinced it's entirely dry. The truth is, we don't have enough data yet. We need to visit one of these sites up close, drill into the slope, see what's actually there. But planetary protection rules make that tricky. If there is liquid water, even briny water, we need to avoid contaminating it with microbes from Earth. What we know for certain is that Mars has enormous amounts of frozen water. The polar ice caps are the obvious reservoirs. The northern cap is mostly water ice mixed with layers of frozen carbon dioxide and dust. During summer, the carbon dioxide sublimates, revealing the water ice beneath. The cap is roughly 1,000 kilometers across and up to 3 kilometers thick in places. If you melted all that ice, you'd have enough water to cover the entire planet to a depth of several meters. The southern polar cap is smaller and composed mostly of carbon dioxide ice sitting on top of water ice. It's colder in the south, cold enough to keep carbon dioxide frozen year-round. But beneath that dry ice lies more water ice, permanently frozen in the Martian permafrost. And the ice doesn't stop at the poles. Ground-penetrating radar from orbit has detected massive sheets of ice buried beneath the surface across huge swaths of the Martian mid-latitudes. Some of these ice deposits are just a few meters below the dusty surface. In some regions, the ice is over 100 meters thick. It's like Mars has underground glaciers, relics from wetter times.
now preserved beneath protective layers of dust and rock. In 2018, the European Space Agency's Mars Express orbiter detected something even more intriguing: a bright radar reflection beneath the southern polar ice cap. The reflection was consistent with liquid water, a subglacial lake similar to Lake Vostok in Antarctica, sitting beneath more than a kilometer of ice. The discovery was controversial. Some scientists think it's real. Others argue the reflection could be caused by clays or other materials. Additional observations in later years found more potential lakes in the same region, which either strengthens the hypothesis or suggests the radar is detecting something else entirely. We won't know until we can drill through the ice and see for ourselves. But here's what makes the water situation on Mars so critical for future exploration. Water is heavy. Launching water from Earth to Mars would cost tens of thousands of dollars per liter, maybe more. It's simply not feasible to bring enough water to support a human crew for months or years. You need to find it on Mars. And fortunately, it's there, locked in ice, mixed into minerals, possibly even flowing underground in briny aquifers. The key is extraction. NASA's Perseverance rover carries an experiment called MOXIE, the Mars Oxygen In Situ Resource Utilization Experiment. It's a small device, about the size of a car battery, that extracts carbon dioxide from the Martian atmosphere and converts it into oxygen. Between April 2021 and September 2023, MOXIE ran 16 times, producing a total of about 120 grams of oxygen. That's enough to keep an astronaut breathing for roughly 4 hours. More importantly, it proved the technology works. Scale it up, and you could generate all the oxygen a Mars base would need just by processing the local atmosphere. Water extraction would work similarly. Robots could excavate ice-rich soil, heat it to release water vapor, condense that vapor into liquid water, then purify it. Or drill into ice deposits and melt the ice directly. The water could be used for drinking, growing food, and producing rocket fuel. Split water molecules into hydrogen and oxygen, and you have propellant for the return trip to Earth, all sourced locally. No need to ship it from home. The Martian water story is far from complete. We know water shaped this world. We know it's still there, hiding beneath the surface and locked in ice. But we don't fully understand where it all went, how much remains, or whether any of it is accessible enough to support human exploration. Every new mission adds pieces to the puzzle. Every radar scan, every drill sample, every analysis brings us closer to understanding this planet's hydrological secrets. And those secrets matter, because they determine whether humans can actually survive there. Which brings us to the biggest question of all. Should we even try? Elon Musk wants to die on Mars. Not on impact, hopefully. He's stated he wants to retire there, spend his final years on a world he helped colonize. It's an audacious vision. Send millions of people to Mars over the next few decades, build cities, terraform the planet, make humanity a multi-planetary species, and he's putting his money behind it. SpaceX's Starship is designed explicitly for Mars missions, a fully reusable rocket capable of carrying over 100 tons of cargo to the Martian surface. The timeline is ambitious to the point of absurdity. Musk has suggested uncrewed missions could launch as early as 2026, taking advantage of the next Earth-Mars transfer window. Crewed missions potentially by 2029. Build a self-sustaining colony by 2050. Most aerospace experts think this timeline is wildly optimistic. But then again, most experts thought reusable orbital rockets were impossible, and SpaceX proved them wrong. So maybe, just maybe, Musk will surprise us again. The technical challenges are enormous. Getting to Mars is the easy part. Landing is harder. The Martian atmosphere is thick enough to create friction during descent, but too thin to slow a spacecraft down effectively with parachutes alone. Perseverance used a complex system involving a heat shield, a supersonic parachute, and a rocket-powered sky crane that lowered the rover on cables. Starship will need to land using its engines, performing a controlled descent with minimal atmospheric assistance. It's been done with smaller craft. Scaling it up to a ship carrying 100 tons of cargo is another matter entirely. Then there's the problem of fuel. Starship needs propellant for the return journey. Launching that fuel from Earth defeats the purpose. So, SpaceX plans to produce it on Mars, using in situ resource utilization. Extract carbon dioxide from the atmosphere, bring hydrogen from Earth, or split it from Martian water. Combine them using the Sabatier reaction to create methane and oxygen. Methane for fuel, oxygen for oxidizer. It's chemically straightforward, but building and operating a fuel production facility on Mars, especially one reliable enough to bet your life on, is a massive engineering challenge.
The human factors are even more daunting. A trip to Mars takes about 7 months each way. 7 months, cooped up in a metal can with the same people, exposed to cosmic radiation, dealing with zero gravity. Bones weaken, muscles atrophy, the cardiovascular system deteriorates. And that's before you even reach Mars. Once you land, the radiation problem gets worse. The Martian surface receives about 50 times more radiation than Earth's surface. Over a year, an astronaut on Mars would absorb radiation equivalent to getting a full-body CT scan every few days. Long-term exposure would significantly increase cancer risk. You could build habitats partially underground or cover them with Martian soil for shielding. That helps. But anytime you're outside, in a spacesuit, doing repairs or exploration, you're accumulating dose. And unlike on the moon, you can't just abort and come home if something goes wrong. The planets only align for efficient travel every 26 months. If you miss your return window, you're stuck for 2 more years. No rescue mission is coming. The psychological challenges might be the hardest to overcome. Mars colonists would be further from Earth than any humans in history. Communication has a delay of anywhere from 4 to 24 minutes one way, depending on orbital positions. You can't have a real-time conversation. You can't call home when you're having a bad day. You'd be isolated in a way that's difficult for most people to comprehend. And if you're part of the first wave, there's no going back. The mission architectures being discussed involve one-way trips, at least initially. You'd leave Earth knowing you'll never see it again. Never feel rain on your face. Never swim in an ocean. Never breathe fresh air without a helmet. Some people are excited by that prospect. The ultimate adventure. A chance to be a pioneer. But there's a reason suicide rates are high in isolated research stations in Antarctica. And those people can go home after a year. Imagine the same isolation but permanent. And deadly. Step outside without a spacesuit, and you have about 90 seconds before you lose consciousness from hypoxia. Your blood wouldn't actually boil, despite what movies show, but the lack of oxygen would kill you fast enough. Then there's the question of resources. The most optimistic estimates suggest getting a single person to Mars and back costs millions of dollars. Establishing a self-sustaining colony of thousands would cost hundreds of billions, possibly trillions. Where does that money come from? Government space agencies have budgets, but they're limited and subject to political whims. NASA's funding has been essentially flat for decades. The Artemis program to return to the moon is already struggling with cost overruns. A Mars program would be far more expensive and take much longer to show results. Private companies like SpaceX can supplement government funding, but they need revenue streams. Tourism? Maybe eventually, but who can afford a ticket to Mars? Mining? Mars has resources, but nothing so valuable it's worth shipping back to Earth across millions of kilometers of space. The economic case for Mars colonization is weak, at least in the near term. It's not about profit, it's about survival. Making humanity multiplanetary so that a single catastrophe can't wipe us out. A noble goal, but is the risk worth it? Some argue we should focus on fixing Earth's problems before running off to another planet. Others say we need a backup plan in case Earth becomes uninhabitable. The debate gets philosophical quickly, and there are legal and ethical questions nobody has good answers for. Who owns Mars? The Outer Space Treaty says no nation can claim sovereignty over celestial bodies. But what about private companies? What about individuals who establish settlements? SpaceX has already stated in their terms of service that Mars would be governed by self-determination and direct democracy, not Earth-based governments. That's a bold claim with no legal foundation. If disputes arise, who adjudicates? What laws apply? It's going to be messy. Then there's the question of contamination. If Mars has life, even microbial life, we have an ethical obligation not to destroy it. But human missions are inherently contaminating. We carry trillions of microbes in and on our bodies.
We can't sterilize ourselves without dying. If we establish a colony, we'll inevitably introduce Earth organisms to Mars. They might outcompete native Martian life. We could accidentally cause the first interplanetary extinction event. Some scientists argue we should hold off on crewed missions until we've thoroughly searched for Martian life with robotic missions. Others think the risk is acceptable because the scientific and inspirational value of human exploration outweighs the potential harm. There's no consensus. Despite all these challenges, preparations continue. NASA is developing new spacesuits for Mars, testing habitats, running analog missions in Mars-like environments on Earth. SpaceX is iterating on Starship, each test flight bringing them closer to an operational system. The United Arab Emirates, China, and India all have Mars programs with increasing ambitions. It's possible that within our lifetimes, humans will walk on Mars. Whether they'll stay is a different question. But maybe that's okay. Maybe Mars isn't meant to be a second Earth. Maybe it's meant to be a laboratory, a place to learn how planetary systems work, a testing ground for technologies we'll need when we eventually venture beyond the solar system. A reminder that we're capable of great things when we work together toward a common goal. Mars has already taught us so much about planetary formation, climate change, and the limits of habitability. Imagine what we could learn with people on the ground, exploring caves, drilling deep, analyzing samples with sophisticated equipment. The scientific return would be extraordinary. Here's what we know. Mars was alive once, in a sense. It had oceans and rivers, and maybe even life. Then it died. But its corpse holds secrets. Secrets about how planets evolve, about what makes a world habitable, about our own future as we face climate change on Earth. Mars is a warning and an opportunity. A cautionary tale about what happens when a planet loses its magnetic field and atmosphere, and a chance to prove that we can overcome impossible challenges when we have to. The dead planet isn't quite dead. Beneath the surface, water waits. In the rocks, organic molecules sleep. And in our telescopes, on our launch pads, in our dreams, Mars calls to us. Not because it's easy, not because it's profitable, but because it's there. Because we're curious, because we need to know if we're alone, and because somewhere, deep in our DNA, we remember what it was like to stand on the edge of the unknown and step forward anyway. Mars killed its oceans. Mars lost its air, but Mars survived. And maybe, just maybe, we can learn from its mistakes. Maybe we can take what this dead world teaches us and use it to keep our own world alive. Or maybe we'll join Mars in silence. Either way, the red planet waits, patient, eternal, ready to reveal its final secrets to whoever is brave enough to come looking. So hit that subscribe button if you want to follow along as we continue exploring the mysteries of our solar system. Hit that like button if this story blew your mind. Because the universe is full of stories like this. Dead worlds that used to live, living worlds that might soon die, and us, somewhere in between, trying to figure it all out before our own time runs out. Thanks for listening, and keep looking up.